So next up, we're going to talk about some polar functions that do not convert nicely into Cartesian coordinates. The first of which is going to be referred to as a cardioid. The prefix cardio meaning heart, and the suffix oid meaning looks kind of like that thing. So this will be referred to as a cardioid. The cardioid takes on 4 different possible forms based off of whether we're using a cosine or a sine. The positives versus negatives and the pluses versus minuses, all that those things do is dictate where the extreme point can be found on each of these things, and therefore dictates the orientation. So an example of a cardioid would be something like r is equal to 3 plus 3 times the cosine of theta. Now with that in mind, rather than converting this into x's and y's, what I'd like to do is just keep this in polar coordinates and see if we can graph this using only polar coordinates. So as far as angles I'd like to use, we'll go for the classic angles from the unit circle. All of our quadrantal angles, if you will. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. So at a theta value of 0, this would be 3 plus 3 times the cosine of 0, which would be 1. At pi over 2, this would be 3 plus 3 times the cosine of pi over 2. Cosine of pi over 2 is 0, so we get a radius of 3. At pi, this would be 3 plus 3 times negative 1, which of course would be equal to 0. Cosine of 3 pi over 2 is 0, so we would get an r value of 3. And then 3 plus 3 times the cosine of 2 pi. Cosine of 2 pi is 1, giving us an r value of 1. Or excuse me, 6. Cosine of 2 pi is 1. 3 plus 3 is 6. I do math. All right. So what I'd like to do is plot all of these points together in polar coordinates. Here is an r value of 6. At pi over 2, we had an r value of 3, so in the direction of pi over 2, we'll go up 3 units. In the direction of pi, we got 0. That'll be a point right at the pole. In the direction of 3 pi over 2, we got an r value of 3. And then in the direction of 0 or 2 pi, we once again get an r value of 6. Now the idea is the value of r should be smooth and continuous, since the cosine is a smooth continuous function, and based off of these values I think it's safe to ascertain that this thing will never be a negative value, meaning that it will never actually cross through the pole. Now as such, what you're going to wind up getting is something that looks like this. Nice x-axis symmetry on it. And as you can tell, this thing looks kind of like a heart. So we're definitely going to not call it a buddyoid or an asioid. It's definitely a cardioid. Now, this equation doesn't convert particularly nicely into Cartesian coordinates, so we're not going to bother with it. Now, I mentioned earlier about the extreme point. You'll notice that we had a positive coefficient and we had a cosine. And when I'm thinking in terms of trigonometry, I associate cosine with the x variable, a horizontal variable, and I associate positive with being the right-hand side. And you'll notice that the extreme point, which is the maximum value of r, we'll call that the extreme point, happens to be in the same direction. That also lets me know that if I were working with r equals a plus a times the sine of theta, the extreme point would be in the upward direction. We would wind up with something that looks kind of like this for a cardioid. If we had r equals a minus a times the cosine of theta, once again cosine tends to be horizontal, and with that negative, the extreme point will be on the negative side. And finally, r equals a minus a times the sine of theta, we would see the extreme value in the downward direction. And just when I thought I was getting really good at drawing these cardioids, they started looking like butts. Ah well, what can you do? So that is the first example of something that has no good conversion into Cartesian coordinates. Let's move on to a second example. Second example, I don't actually speak French, so I have to rely on what I have heard. Apparently there's this cool C in French with a tail on it. And this is pronounced limaçon. Limaçon takes on one of the following forms. R is equal to a plus or minus b times the cosine of theta, and r is equal to a plus or minus b times the sine of theta. The one thing to create a limaçon is that you need to make sure that your a value is less than your b value. So with that in mind, let me give you an example of one such limaçon. Our last example we did cosine, so this one let's do a sine. So let's do r is equal to 1 plus 2 times the sine of theta. So predictions that I'm already going to make, I am going to predict that the extreme point is going to be in the upward direction due to the fact that we have a sine and we have a positive. So once again, I'm going to create a little table where we can use several familiar values of theta. Pi, 3 pi over 2, and 2 pi. And we'll use these values to figure out sort of what this graph looks like. So our value is going to be 1 plus 2 times the sine of each of these angles. So the sine of 0 is 0. Pi over 2 gives 1. Pi gives 0. 3 pi over 2 gives negative 1. And 2 pi gives 0. Simplifying each of these r values, we are going to get 1, 3, 1, negative 1, and 1. Now the thing that's different between the limaçon versus the cardioid is that you'll notice that the r value dips into some negative values here. This is due to the fact that the a value was less than the b value. As such, we're going to see this thing cross through the pole. So in the direction of 0, r goes out 1 unit. In the direction of pi over 2, r goes out 3 units. In the direction of pi, r goes out 1 unit. In the direction of 3 pi over 2, however, r goes out negative 1 units. So that'll take us back up here. And finally back to 2 pi, that'll be out 1 unit. I'm going to do my best with this, but it's been a while since I've drawn a limaçon. Let's try this out. Okay, like this, and then like that. Cool. Alright. So, again, you can expect the limaçon to pass through the pole to wind up with a couple of negative values, as well as a lot of positive values. So the limaçon is essentially created by two loops. These are referred to as the outer loop, and this of course would be the inner loop. As a cat owner, I can respect something that holds many loop, brother. Now again, if we were to mess with the orientation a little bit, we could get the extreme point to be in any of the other 4 directions. Extreme point is in the upward direction, which again is the prediction that we made based off of the fact that the sine had a positive coefficient. Now, suppose that I wanted to determine where it crosses the loop, or excuse me, where it crosses the pole. Where does this cross the pole? So this is going to cross the pole anytime the r value is 0. So what I'm going to do is set my r value in this equation equal to 0. I'm going to solve for the sine. So subtract 1 and divide 2 on both sides. We get that negative 1/2 is equal to the sine of theta. There are 2 points on the unit circle where the y-coordinate achieves a negative 1/2, and that would be at 7 pi over 6 and at 11 pi over 6. Now 7 pi over 6 is in between pi and 3 pi over 2, and you'll notice that this is where the r value dips from positive to negative. 11 pi over 6 is between 3 pi over 2 and 2 pi, and that's where, again, it crosses from negative back into positive. So essentially what we have going on is if we wanted to figure out these two angles right here, where it's dipping through the pole, those two angles would be at 7 pi over 6 and at 11 pi over 6. So another example of something that does not convert nicely back into Cartesian coordinates. For a third and final example of something that does not convert nicely, these are referred to as roses. Roses, however, is kind of a general term. They do tend to look floral in nature, but roses they definitely are not. So r is equal to a times the cosine of n theta, or r is equal to a times the sine of n theta. Now, this is where n is going to be indicative of a positive integer. And generally, we only consider the cases of n being greater than or equal to 2. Otherwise, these things would be considered circles. So an example of a rose would be something like r is equal to 3 times the sine of 2 theta. Now, to explain what goes on with a rose, I think that I can sort of explain what was going on with the limaçon. Now, when it came to the limaçon, we were able to figure out where it hits the pole by setting r equal to 0 and then solving for the appropriate variable. Well, a rose also hits the pole many, many times. Hits the pole at, well, let's figure it out. 0 is equal to 3 times the sine of 2 theta. Divide 3 on both sides, and we find out that the 3 isn't really a relevant thing. So sine is equal to 0 every time we're at an integer multiple of pi. So we'll call that k pi, where k is any integer. Therefore, theta is going to hit the pole every time we're at a multiple of pi over 2. So to set up what this looks like, that means that at 0, it'll be at the pole. At pi over 2, it'll be at the pole. At pi, it'll be at the pole. And at 3 pi over 2, it'll be at the pole. Now at theta equals 0, the r value will be 0 as well. As theta starts to increase, the value of r will be positive. So in between 0 and pi over 2, this thing is going to create what we call a petal for the rose. The extreme point that we get out here is going to be where r is equal to 3, as is dictated by this. The maximum value of the sine is 1, so the maximum value of r is 3. Then it comes back to pi over 2, where the r value starts to be negative. So in between pi over 2 and pi, we wind up with an r value that is negative. And we see that this thing will be created in quadrant 4 rather than quadrant 2. Then it'll continue into quadrant 3 using positive values of r. And then through quadrant 4, it'll actually be giving us negative values of r, sweeping out a petal in quadrant 2. Now, when we had 2 theta, we wind up with a rose with a total of 4 petals. If n was 3, we would get 6 petals. If n is 4, we get 8 petals. And more generally, if this value is n, we're going to wind up with 2n petals. Actually, I think I might be mistaken there. I think that it's different between odd and even values. What I would encourage you to do is switch your calculator over to polar mode and just mess with a whole bunch of different values and see what you can come up with. Now, if we had changed this ever so slightly to be r is equal to 3 times the cosine of 2 theta, then rather than starting at the pole, we would actually be starting at an extreme point. If you do the same calculation as what we did for the sine, you would actually get that pi over 4 plus k pi is going to be where we see our intersections with the pole. So extreme points are going to be on the axes, and petals are going to have their boundaries at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So it just kind of tilts the roses ever so slightly. Man, those are complicated to draw. In section 10.4, we'll talk about finding area of such things, and it'll be kind of fun.